Okay, so good evening. So we'll start the live session for week 3. Okay, so today we'll discuss some problem which are based on the week 3 NPTEL videos. So they are basically the time response for the second order and first order system. So the time response means it actually consists of, like, we can separate them as an natural and forced response. So natural response means without any external input. So the system is derived only through this initial condition, and the forced response means you just make this initial condition zero and give some kind of input to the response then the response of the system will be called as a forced response. So another classification is through yeah. So can you mute? Okay. So another type of classification can be, the response can be classified into transient and steady state. So you already know that, like, the steady state means as the time goes to infinity. That means as you progress in time to a large amount of times, after that, if the system settle down, if possible, that then this response is called as the steady state response, right? So and the response up to the steady state that actually dies out after some times is called the transient response. So you had, like, for the transient response, to test that, you apply some kind of test signal. So it could be like some kind of shock that is actually represented by impulse, or some sudden changes, so step input, or the gradually changing, that is the ramp input, or some kind of fixed acceleration, that is the parabolic input. And you just verify, like, systems. So through that response you classify some system, so you have some kind of knowledge how that system actually behave through transient. And the steady state means at the time progress, as the transient decays out, as time become very large, mathematically it can be represented by time goes to infinity. So your system gives settle down to some kind of a response. That means that will be the response as the time is very large, so your transient response dies out. Then you have this steady state response, and you just verify whether your steady state response is what you wanted to get from that system, it is following that system reference input, or it's not. So then you have some kind of error between that input signal that is you applied and that output what is desired there, and you call that as a steady state error. And you classify your system according to your types of system, as you have already seen. And then you just characterize your system through this steady state error, like how it will behave in the steady state. Okay, so we'll discuss about some problem on this topic. And also you have learned this block diagram, right? Initially you have some block diagram representation, and you simplify them using either block diagram reduction or signal flow graph. Okay, so we'll discuss all this problem, some simple problem on that. Okay, so this problem one. So you have a simple block diagram representation of one system. So you just simplify and find the transfer function. Okay, so yeah, so you try first for poles, then we'll discuss. So you can try you can use either block diagram reduction or signal flow method. Okay, so I'm yeah. You can see the poll and you can take some time and answer, then we'll discuss about this. Okay, so any doubt on the question or something, then you can ask. Okay, so just a basic question on simplifying. Okay, yeah, I hope I'm audible also, right? Okay, yeah, you can answer through poll, right? Okay, so then we'll discuss this. Okay. Ending this poll, and we'll discuss this problem. So we can use, as I said, we can use both block diagram reduction, or you can use the signal flow formula also, right? So let's first try with block diagram reduction, then we'll try also with signal flow. So as you can see, one thing you can easily simplify is this block. It is just simply the two signals that are summed there inside, right? So you just can add them, this gain, and you can replace this with a simplified term, which is just one. Instead of that, you just replace it with some block. So then your simplified version will be okay. You had this UPS, this is and 1 by S YS, and you have this signal with negative feedback 1, and this inside that can be simply replaced by S plus 1 by S, because both signals are added there with positive sign, right? So that is simply S square plus 1 by S. Okay, S square plus 1 by S. Okay, then this is minus this also. Okay, then you can use the feedback formula, right? Only issue is that this point you are taking the signal from that. So if you can just shift this takeaway point from here only, this point here, then it can be the feedback formula can be directly applied. Okay, so okay, so for example, if I take this point, this signal from here, okay, then what should be the value of this block? Can anyone answer? So instead of this point, I'm taking there. Okay, so let the signal value to here be some x1. Okay, initially. So now what will the value after this block 1 by S? It will be x1 by S, right? So initially you are taking that x1 signal, now you are taking x1 by S. So this block value should be something that will cancel out that S. So it will be S, right? Okay, so now again you have this signal here. This signal and this signal are both coming to this one summing point, so they can also be added together, and this minus sign there, so I can have a one block here instead of that. So because initially it was S in the above and plus 1, so I can write also like that. Is it clear? So then you just apply the feedback formula directly. Okay, so what is your GS value here? S square plus 1 by this and this are in the cascade, so you have S square, and the HS value, the feedback one with negative 1 is S plus 1, right? Yeah, negative feedback. So then your closed loop transfer function is what? G by 1 plus GH, right? This transfer function Y by U. So you just simplify them. So instead of G you have this S square plus 1 by S square, and 1 plus GH is this s plus 1 s square plus 1 is g by s square, and h is s plus 1. Okay, we just simplify them. So I am writing here. So the transfer function is, so above term is s square plus 1 by s square, and the denominator is you have s square plus s cube plus s square plus s plus 1 by s square. So here s square plus 1 by s square s cube plus 2 s square plus s plus 1. So this is your transfer function. Okay, so this answer is s square plus 1 by s cube 2 square. Yeah, so we have B, right? So let's try with signal flow now and see whether we are getting the same answer or not. Okay, so then for signal flow, then you have to identify what are this important signal. Okay, that need to be represented, and your given you just represent with arrow mark with some term, right? This is block. So that means here we have some signal here. This is summing point, one signal is there. Another signal is this pickup point. Okay, and another signal is this, right, where you are picking this y signal and giving it as feedback. So just write the signal flow representation of that. So at this point you have one input is u. Okay, another is you're feeding back some signal there, we'll write that, and another signal is this one also, we'll just write. Okay, and inside that we have this and this, you can just write as an addition, because this is just simple addition, s plus 1 by s. Okay, then you are picking that signal here and you are giving this signal as -1, so negative feedback, so this gain is -1 there. Okay, and signal flow you can write this is a gain instead of this block representation. So this gain is s plus 1 by s, or which is equal to s square plus 1 by s, right? And after that there is this gain, right, this 1 by s. So you have another gain 1 by s, this with arrow, and then this signal is again feedback with minus sign here. So this gain is -1, and then you have this output ys. Okay, so now you have this signal flow representation. So how many forward paths are there? From u to this output y. One, right? So one forward path, and we have how many loops? These arrows are clear. So we have two loops, right? This one, this above one there, and this below one, and this above one, right? This one and this one. So you just write the forward path gains and this loop gains also. So the forward path gain is simple, this forward path, right? So I will use some color. This one forward path, right? This whole. So the gain of this forward path is what? The simple s square plus 1 by s square. This multiply this gain multiplied with this one, and the two loops are there. So let denote it p1, and loops l1 and l2. Okay, so one loop gain is what? This green color loop, which is -1 s square plus 1 by s and 1 by s, right? So it is minus of s square plus 1 by s square. And another loop gain is this yellow one, right? So this is s square plus 1 by s negative sign. Okay, so these are this loop, and because both are touching with each other, so there is not two loop, or because only two loops, so there is not two loops which are not touching with each other. Then you just apply this Mason gain formula. So, and if you just omit this forward path p, then there is no other loop, right? So both loops are touching this forward path. So you have this formula for that, right? Pk this transfer function. So you just apply. So in the numerator we have only one forward path, and because both loops are touching with each other, so this delta k will be, for that will be 1 only. So here a square plus 1 by a square, and in a denominator we have 1 minus these two loops, single loops, loops taken one at a time. So this minus minus will be plus because both have negative sign. So here a square plus 1 by a square, another term is a square plus 1 by s, right? So this, you just simplify them. So you have a square plus 1 by a square, and we have a square plus a square plus 1 s cube plus s by a square. So again you get a square plus 1 by s cube plus 2 s square plus s plus 1, right? So again you get the same answer. Okay, so whether you use block diagram reduction or this Mason-Gain formula, you will get the same answer. Okay, so the next question is again you just use that Mason-Gain formula to find this gain of this. The gain means this transfer function y by r, okay, for this network signal flow graph. So you can answer through a poll. So I am starting, then we'll discuss. Okay, so answer through a poll. Just identify the forward paths and the loops, then it is just clear, right? Just use that formula. Okay, so you have how many forward paths are there? From R to Y. Okay, let's discuss this. We'll discuss. Okay, so how many forward paths are there? Can anyone answer?
Six.
Forward paths, how many? Okay, so forward path means you does not traverse through one nodes more than once. Okay.
Two forward paths.
Right. Okay, so you may be counting these loops, right? Then you are just saying like traverse this. So forward path means you don't travel through one node more than once. Okay, so because in this, if you just go like this, okay, like this and go this, then you have traversed these two nodes, right, more than once, like 2 times to be exact. So this is not a forward path. Okay, so you just see if you can go from this R to Y, that is the between whom you want to find this transfer function, how you can go where you don't travel each node more than once. Okay, so one path will be like straight, this one, another path is through this. Okay, other paths will have like more than, you will travel the node more than once, right? So these are not forward path other than this. So you have only two forward paths. Okay, then you identify the loops. So first write this forward path gains. So this one state one, this gain is what, 3 times 4 times 5 times 1 and 1, so it's like 20 60. Okay, so this 1 this gain is 60. Okay, then other path which have gain, this one, this is 6, right? So then let denote as P2, so it is 6. So how many loops are there?
Three loops, sir.
Okay, yeah. So is it only 3 loops or more than 3 loops are there?
Yeah, 4 loops, sir.
Okay, so these 3 are very clear, right? These are 3 loops. So then see, are any other loops are present? So one loops will be, so again loops means you start from one point and you end up on the same point without traversing any nodes more than once. Okay, so one, let you start from there, then you can go like this, and you can go like this and this, and you can this. So this is also another loop, right? The fourth one. So you have 3 loops. You can easily identify 3 loops here, this one, this one, this one, and other loops is this outer ones. You can go through this, reach this node, then you traverse this, and you reach this. So this is also another loop. So there are 4 loops. Okay, so just write this loop gain. So this loop gain, let L1, L2 and L3. So these are simple, -3, -4 and another -5, and this last one, this outer one, this one. Okay, I'm denoting with L4, so which is 6 times -1, -1, -1, so here -6. Okay, then how many loops there are, like 2 taken at a time that are not touching with each other? So how many loops are there that are not touching with each other if you take in pair?
Huh? Two non-touching loops.
Yeah, one pair of non-touching loops, right? So this one and this one. Others are like, if you take this, they are touching with each other. This also, this touching with each other, and this bigger one is touching with all 3. So you have only 2 loops, and their product will be this one and this one will be 15, right? So these are L1 and L3, so it is 15. Okay, then if you delete this forward path, okay, this forward path, you see that all these loops are touching with this forward path, right? And so for this forward path, this gain will be 1, right? And for other forward path, this one. So which loop is not touching to that forward path?
-4 loops.
Yeah, this loop is not touching. So then for that, let's write this delta 2. So delta 2 will be 1 minus loops that are taken 1 at a time, then plus product of these loops that are taken 2 at a time, and so on, after deleting this path, right? So you delete this path through this node. So this node will be gone, this node will be gone, because you are deleting this path. Okay, so only this loop will be there for. Okay, so you write this gain delta 2, this will be what? 1 minus this loop gain is -4, that is actually not touching, so it is 5. Okay, now we have already all this required quantities or terms. Then you just apply this gain formula, the transfer function. So this is just what, all these forward path gains times this delta k by this is the transfer function. So you have in the above term this 60 times 1, this p1 times delta 1, plus this 6 times, this is the gain 5 also we have to compute this delta, right, for this denominator, which is simply again 1 minus this single loop gains, which are 3 minus 3 minus 4 minus 5 minus 6. So all will be plus with minus sign. So we have 3 plus 4 plus 5 plus 6, and this another 2 loops taken at time. So this is what? So 1 plus this is 7 plus 11. So it is what? 18, right? 1 plus 18 plus 15. So we have total 34, right? So this is below 34. So it's equal to above is 90 by 34, or you can simplify 45 by 17. Okay, this one. Okay, I have a space there. Okay. Anyway, so is it clear, this question? Okay, so you just identify these loops. This is first forward path, this 2 forward path, and these loops all. Then you identify which loops are not touching with each other, 2 taken at a time, 3 taken at a time, and so on. Okay, then you identify the loops that are not touching the paths. Okay, that means if you do not omit this forward path, one forward path, which loops will remain in the system, okay, in the signal flow graph. Then you take this delta gain for that forward path that is you have in the numerator for that, and then just simply apply this Mason-Gain formula. That's all. But you have to just careful when identifying. Only things you can do is some kind of a trivial mistake. Okay, nothing else will be there. So you have to be very careful when identifying. That's all on that. Okay, so then we move to the next question. So we have two statements. So for first statement, we have a you are considering only stable closed loop second order system. Okay, so the first statement says that your settling time is inversely proportional to your damping ratio, and the second statement is saying that your peak overshoot will decrease with increase in the damping ratio. Okay, then you have to identify like which option is true, whether this both statements are true or one statement is true and other is false, or both are actually false. Okay, so question 3 you can try with like answering through poll, then we'll discuss. Okay. So you can just write the formula for that, and you can just analyze and see like if these statements are correct or not. Okay, so you write the formula for settling time. So settling time means where you can use either two sorry, plus minus 2% this tolerance, or plus minus 3% 5% tolerance. Okay, any formula, and see how this settling time is related to damping ratio, and similarly you have this peak overshoot, how it is related to. Okay, yeah, you can see the poll, right? You can answer through this poll also. Okay, okay, so yeah, just straightforward question, so we'll just discuss. Okay, ending this poll. Okay, just write this relation for the both. Okay, like this settling time and the formula for settling time and your peak overshoot. Okay, for settling time you have only okay, either for 2%, or you have like for 2% tolerance, right? This is the formula for zeta omega n. So you just see that it is inversely proportional to your this damping ratio, the settling time. Okay, so the statement 1 is correct, right? For statement 2, you have this overshoot, right? This MP, which is given as a fraction, it will be e to the power minus eta pi by 1 minus eta square root. Okay, e to the power this whole term. Okay, so you just see how this this overshoot is actually related to this damping ratio. So you can just take some values and verify also. Like for example, if you take this zeta to be 0, then what is this overshoot? You just plug in that zeta equal to 0 there, damping coefficient, damping ratio. we have what? E to the power, yeah, 1, right?
One.
So this is 0 by 1, right? So it is 1. Then take some intermediate values also you can take. For example, you can take zeta is equal to half. So half means it will be pi by 2 by, this will be 3 by 2, right? Square root of 3 by 2. 1 minus 4 by 1 by 4, so it will be this, or e to the power minus pi by 3. Okay, so again you can take one value zeta equal to 1, so it will be extreme value, so it will be, yeah, 0, right? So it's minus infinity, almost like 1 by divided by 0. Okay, so that's the limiting sense, you cannot write directly e to the power minus infinity, so it's almost 0 as zeta goes to 1, right? So its value is actually decreasing. So if you plot that, so this is zeta, so it's 1 for this is 0 value, and 1 this, like that, decreasing some, decreasing type curve will come. Okay, so your peak overshoot will decrease with increasing the damping ratio, right? As you increase the damping ratio. So statement 2 is also correct. Okay, so we can move to next question again. So you have a steady state error is given 0.05 for unit step input. So then you know that unit step response, the steady state error is finite. Okay, so then your system this position error will some value, right? Position error coefficient, so you have to determine that. So again, very simple question. So yeah, you answer that all. Okay, so very simple question, you just plug in your value and you get that answer. Yeah, so okay, so discuss this because this is very simple question. So the formula for like steady state error is for what? This is a formula, right? Equal to your steady state error value, so which is 0.5, and you just simplify it. 1 plus kp will be equal to what? This is 1 by 0.05, 20, so your kp value will be the position error constant kp, which is actually 20 minus 1, 19, right? 19. Okay, so then we move to the next question. Okay, so for this question you have a second order system. Settling time is given for plus minus 2% tolerance, which is 7 seconds, and peak time is 3 seconds. Then the poles, the location of the poles are what? Okay, so this question number 5. Yeah, so you can answer through poll. Okay, okay, so I'll discuss this question. Okay, so For second order system, okay, so we are talking about only underdamped system right here, because you have this peak time is only defined for underdamped system, right? If you remember from this lecture videos. So we are just considering underdamped system, and for the underdamped system you have complex conjugate poles in the left hand side, right? So second order system, you have only pair of conjugate poles, okay. So for, and that pole location will be what? It will be given by this omega d, where omega d is a damped frequency, which is okay. So if you can just determine this damping ratio and this natural frequency, then you just have this location of this poles, okay. So you are given settling time, that is Ts, for this 2% tolerance. This formula is what? This one, right? So, and that is given as 7 seconds. So you have zeta omega n equal to 4 by 7, and that value is for 0.571, okay. Similarly, you are given peak time, which is simply omega d, okay, and which is given 3. So you just obtain this omega d equal to pi by 3, which is again you can just compute it, and it's 1 point something 047. So your pole locations are this, so that means minus of 0.571, this is this one, and this is omega d plus minus j 1.047, okay. Okay, so next problem. So you have a negative non-unity feedback, okay. Your HS matrix in the feedback is not unit, okay. You are given this transfer function, this is forward transfer function GS, and this feedback transfer function HS values are given. So then you have to determine this K1 and K2 such that you have a peak overshoot of 20% and peak time is 1 second, okay. Again we are just considering underdamped system, which is clear from the given data, because you are given peak overshoot and peak time, okay, that are valid for only underdamped system. And then question problem is you can answer through poll first try, then we will discuss. Okay. So I hope this question is clear, okay. So what you can do is first find the closed loop transfer function. So then you know the standard transfer function for the second order system. So you can find that damping ratio and this natural frequency, that's zeta and omega n. Then you can find a relation between K1 and K2 with them. So you just solve them, you will get that K1 K2 value, okay. Question is clear? Any doubt you can ask regarding question also, if something is not clear. Okay, so please try, then we'll discuss. Okay, just try. Okay, so let's discuss this. Okay. Okay, so you are given this g and h value, so you can just write this closed loop transfer function, right? So for this negative feedback system, the closed loop transfer function is what? Simply g by 1 plus gh, right? So you just write that transfer function first, closed loop transfer function. So for g value this and h value this, so here k1 by s times s plus 1 in the numerator, in the denominator you have 1 plus gh, so this is k1 times this one 1 plus k2s by s into s plus 1. Okay, you just simplify them, so it will be k1 by, it is s square plus s plus k1 k2 s plus k1. Okay, this numerator denominator term will cancel out, s into s plus 1. So you have this is the closed loop transfer function, or you can just simply write it k1 by s square plus 1 plus k1 k2 s plus k1. Okay, so if you remember, the standard form of this transfer function is what? Second order system, omega n square by s square plus 2 zeta omega n s plus omega n square, right? So then you can simply find this k1, just compare this coefficient and you can find. Okay, so for that you need this zeta and omega n. Okay, so first we can just compute them with the given data. We have like peak overshoot and you are given the peak time. Okay, so for that first we write this peak overshoot formula. Okay, so you have overshoot formula is a, you know, is a fraction. It is given by minus this by 1 minus eta square. So you can just simplify it. You can write the damping ratio in terms of this peak overshoot MP. Okay, so for that you just take this logarithm on the both side, so it will be ln MP ln MP term to minus pi by eta by 1 minus square this. So take the square on both sides, so it is ln square MP equal to pi square eta square by 1 minus eta square, and you multiply this term with this, so you have ln square MP minus zeta square ln square MP, this term equal to pi square zeta square, and you just simplify, take this term on the other side, so it will be pi square plus ln square MP, this time zeta square equal to ln square MP. Okay, then you just simplify this for zeta, that is you just divide this term on other side and take the square root. So when you are taking the square root, you have to be careful what sign you want to find. Okay, so this MP, if it is given in the fraction, that means less than 1, then your ln value will be negative, right? But we are considering underdamped system for which this damping ratio should be positive, so you have to take the negative sign of that. Okay, so here this is your formula. Okay, this ln square here, ln square MP. Okay, so you just put this damping overshoot, the peak overshoot what is given is 20%, that means in the fraction it is 0.2. you just find this damping ratio there, just put this value there, so it is just simply coming out to be for this 0.2 MP equal to 0.2. you can just calculate with calculator, that is using that formula, it is 0.456. Okay, and once you get this eta, then this term 2 zeta omega n, which is equal to this term, right, 1 plus k1 k2. So we can find from that k1 plus k2, but you have to find also omega n for first. Okay, so this omega n also, so that is also you can find from this peak time. So your peak time is, this is pi omega n 1 minus zeta square, so which is given as 1 second. Again you have this zeta value, you can simplify this for omega n, so you can just calculate them. So simple calculation, so it is just something pi by this 3.53. okay, you can just verify them. Okay, simple calculation. So once you find this omega n, then you have this k1 equal to omega n square, so it is 3.53 square, which is 12 point something 461. Okay, and once you have k1,
Sir, how did you get omega n square previously?
what
Omega value for omega n square.
sorry, I cannot hear you. What?
Sir, how have you calculated value of omega n?
Oh, omega n. Okay, let me calculate it. Okay, I thought it is clear. So here you have found zeta value right here, this one. You first use this. Okay, I will again go through. You have this zeta formula for this, right, from this one, percent overshoot, right? Is it clear how we get that damping ratio formula?
Yes, sir.
Huh?
Yes.
Yeah, so you can calculate then, because you are given this overshoot is 0.2, right? So you can find this damping ratio here. Simple put this MP equal to 0.2. So you have what, minus of this logarithm of 0.2 by this pi value, you know this. So you can calculate this damping ratio. Is it clear for damping ratio?
Yes, sir.
So once you get this damping ratio, you have this formula, right? Okay, let me write it again. So your damping ratio you found out to be this, from this formula it is something 0.456, right? Yeah. So then you are given peak time also, right? So peak time, this formula is what, omega d, right? Or you remember this formula, right? Peak time, 1 second it is given. So that means omega n will be what, pi by 1 minus zeta square square root. Okay, and this is zeta value, right? Is it clear?
Yes, sir.
Okay, is it clear or not?
Yes.
Yeah, okay. So then,
Yes, sir.
yeah, you just put in the calculator. Okay, I actually put that in calculator and calculated. This is just simple. Okay, so that value you get something like 3.53. You just have to calculate them. Okay, radian per second. So this, once you get this omega n and this damping ratio, then other things are very clear, right? You just compare this system, whatever you get, with this second order system, standard second order system, and find this coefficient. So your k1 value will be what, omega n square. Once you get this k1, you have this value, and 2 zeta omega 1 is equal to 1 plus k1 k2. So you have k1 value, you have this zeta omega n value, you can just simply calculate this k2 value. Okay, I'm just writing that values. Okay, you can just calculate them directly. Okay, so this is that 1.78 and this d. Okay, okay, so is it clear or you have any doubt? Once you get this, because you know that for once you have damping ratio and your natural frequency, then you can calculate all these parameter values, right? Only you need this zeta and omega value. So whatever data is given, try to find out them, then you can just calculate others values. Okay, so for example, in the second question now, using that value you have to find like rise time and settling time. Okay, you have the same data in the previous question, so you have this with previous data we have what we have calculated, this is equal to 0.456. okay, 0.456 and omega n equal to 3.53. Then you just plug in this value in the formula and you get this rise time and settling time also. Okay, so try this for question 7. Okay, yeah, ask if you have doubt. You have some doubt, right? You can ask. Okay, just use the formula for the rise time and settling time. So you have already given this value, damping ratio and omega n. So you just plug in and then find, right? So the only things you need is this damping ratio and this omega n. Once you have this data, you can like always calculate others values from there. Okay. Okay, so okay, just then use that formulas and just calculate. Okay, straightforward calculation here also. So you just write the formula for the rise time and settling time. So for the rise time, this formula is okay omega t or omega n minus this. So you just plug in the value of zeta here and omega n and you find this value. Okay, this is something like 6 point. Assume this 650. Okay, so this is this rise time and the settling time. Okay, so you just find the settling time. Okay, for like 2%. Okay, I have not written that 2% tolerant, plus minus 2% tolerant. So it is 4 by zeta omega n. So you can just calculate them again. So it is something 2.485 seconds. Okay, so we have B. Okay, this is correct answer. Okay, so any doubt you have writing? Okay, yeah, you joined now. Okay, so I'm using the same values. Okay, from this question. Okay, maybe it's confusing for that. So you are given some system here. Okay, negative non-unity feedback system, and you have this GS and HS values are given. Then with the data you are given peak overshoot and peak time. Then you have to calculate with using that data you have to calculate this problem. Okay, as I have mentioned that you have to use this from there. Okay, so first you have to solve this, which we already solved in the problem 6, right? We have found that zeta and omega n for this problem. So I'm just using that value in the next question. Is it clear?
Yes, sir.
Somebody asked that. Okay, so if you have not seen that, so just to recollect what we have done. So you are given in this first question you are given. So this is a connected question. Okay, so interdependent question. So in the problem 6 we are given peak overshoot and peak time. Okay, so you just use this formula to find because you know that peak overshoot is related to your damping ratio by this formula. Okay, so you can always find this damping ratio once this peak overshoot is given. So once you have this damping ratio, then you can use this peak time formula, which is both omega n damping ratio. So you have already calculated damping ratio, so you can calculate omega n. So once you have this natural frequency and damping ratio, then you can calculate always other values. Okay, so that we are using in the second question. So we have already calculated damping ratio to be this value and omega n to be this value, so which I have written here. Okay, these two values, because we have already calculated using that same data. Then you have this rise time and settling time, so you just plug in that value in the formula. So okay, I hope it is clear. Yeah, you can ask. Yeah, you have doubt? Yeah, you can ask.
Sir,
Yeah.
hello.
Yeah, you can ask. Yeah.
Sir,
Sir, I
I
have
am
written
giving
in chat box, sir.
Okay. Yeah, I assume this, and it is desired the steady state error is for the infinity the value is k specific limit. Okay. Yeah. Yeah, you can use that steady state error formula, right? For ramp input you have just instead of okay. So here what you have given ramp input instead of t you are given 0.5 t, right? So what will be that signal then? Okay, for that if you have doubt, you okay, don't use that steady state or error formula directly. You write the closed loop system. Okay, so once you have closed loop system, you can write that error, and then you just put that use that final value theorem. Okay, is it clear or you have doubt there? Okay, instead of yeah.
Solve this in like. Hello.
Yeah, I cannot hear you. Okay, so what I think is the issue is that
Can you solve this?
yeah, you can
I'm
solve. Yeah,
able to get what I was.
I cannot hear you. Okay, so just try this. Okay, so you have RT equal to 0.5 t. Okay, instead of t as in the ramp signal, you have half t. Okay, so its Laplace transform will be what? 1 by 2 s square, right? So what you do, you have GS, right? And what you are given unity feedback system. So you can write this closed loop transfer function, right? GS by 1 plus GS, HS is 1. Then you take the difference between this reference and the output, that is the error. Okay, you calculate this error signal, and then you, because your error should be below 0.5, so you first find the expression for the error. Okay, so I'm just writing here. Okay, so you have this transfer function because HS is 1 and you are given what? Negative feedback, right? Unity feedback. You have not mentioned negative, but it should be negative. Okay, so you have this, you can calculate this value, then you calculate this error. Okay, this is the closed loop transfer function, that is the u to y, this transfer function. So you calculate this error will be what? This, right? You try this. Okay, then you have this error value, then this you want this error to be below what? 0.1, right? So calculate this error, so then you can use this final value theorem. Okay, because you are calculating the steady state, that means t goes to infinity, so you want this error, let it be inverse Laplace transform be e, you want this, right? Limit t goes to infinity. Okay, so that means s goes to 0, right? So then you just substitute this es and then find it. Okay, so you will have some relation with k, right? Then you solve for that k. Okay, try it. Is it clear or? Okay, so because here, okay, you have this.
Sir, how?
I cannot hear you. Okay, so for this input here only things will be different because your input is, okay, you are taking r to be, so I'm write it r. Okay, your input you have given as r, so this r. Okay, so you have transfer function, then you have y equal to what? This transfer function times this r, right? Input r. So only things difference is here is r value, which is Laplace transfer will be what, 1 by s square. Okay, because you are given 0.5 t. Okay, as you written in the chart. So this only things you have to plug in there and find. Okay, you try. If not, then we'll again solve. Okay, I'm leaving it for you to try it and see whether you can find. Okay, I just given you hint. Is it clear? Yeah. So try it. Okay, and see. So you just because okay, your standard formulas are applicable only when your standard signal, right? Your RT is not here t only; it is half t. So it will be better to in that case you just write this error signal directly from this transfer function. Okay, so there will be no error then. Otherwise you will have some confusion there. Okay, so you just write this transfer function closed loop. Okay, so closed loop transfer function. So then you find this output, which will be again closed loop transfer function times input. Then you find the error, which is this input minus this output. Then you apply this final value theorem because you want this e value, error value, and then you use this limit because error is given to be less than 0.1. So you have already expressed some error, which will be in terms of k. Then you simplify that for k. Okay, yeah. So we'll then move to the next question. Okay, so again the same data I'm using for this question. So you have a negative feedback system and you have to like identify that important is that it is non-unity feedback. Okay, so you have GS and HS value are given. HS is not 1, which is given something value. Then you find this steady state error value. Okay, for this. So just remember that steady state formula that are given, that are applicable only for unity feedback system. Okay, so whenever you apply, you have to be careful on that. Okay, so for question 8, so try this. Okay, see, yeah, again try. The option you have typed is wrong. Okay, so again you try. Okay, so as I marked, this system is not unit feedback. Okay, just think about that. HS is not 1. Okay, you just you can also check again through this lecture video. To apply that formula, you need HS to be 1. Okay, unity feedback, it is non-unity feedback. So one hint will be you can transfer non-unity feedback, okay, to a unity feedback system. Okay, okay, you can type in the poll. You can see the poll, right? You can type, then we will discuss. Okay, just okay, there is no poll you are writing, but that scenario is only applicable for what? If you remember, unity feedback, right? It's not unity feedback system. HS is not 1. Okay, yeah. Okay, so we'll solve. First try. Okay, I'll solve this. Okay, first try. Okay, so hint will be okay, can you convert this non-unity feedback? Okay, your HS is equal to 1 plus K2S, right? So just draw this block diagram. So you have this and like this. Okay, so you have some input, let it be R, output Y. So GS is given this one, G, and your H is given. So G is given, it is K1 by S times S plus 1, and H is given 1 plus K2S with negative feedback. Okay, as mentioned, it is a negative feedback. So can you make it as a unity feedback? Like, can you make it S to be 1 here by some kind of transformation? Then you can apply the formula directly. Okay, so make this H to be 1 by some kind of tricks. Okay, you just use some trick, then you can make this H to be 1. Huh? Yeah, 0. Okay, yeah. So okay, just try. We'll just discuss this question. Okay, it will be clear. Okay, so I will draw this again. So we have GS, which is given as K1 by S into S plus 1. Okay, and you have this HS, which is given as, okay, I will just do for general model, then you can apply this formula directly. Okay, I will write GS and HS because it will be valid for any value of GS and HS. Okay, so this is plus and this is minus. Okay, so what we can do is, okay, we want this HS to be 1. Okay, so I just pick this signal, it's 1. Okay, and I just add it here. Okay, this one, so it's plus minus. Okay, there is no space. Okay, let me, okay, 2 blocks I will add. Okay, this is input R and I am adding 2 blocks. Okay, that is a minus 1 first, plus minus, and this 1 minus. Okay, so is it equivalent to the original system without this 2? Because I have added minus 1 and plus 1, right? Is it clear? Because when you have summing point, these two summing point, after that what will be signal? Because, okay, let's write this. You have two signals that are given to summing point. Okay, like through two transfer function, 1 and minus 1, same signal is given. Then at the summing point, what will be that? They will cancel out, right? This is same sign. One is, okay, 1 minus 1, and is it clear? Okay, why we are doing, it will be clear. First, is it clear? If I have added and subtracted same, right, minus 1 and plus 1 here, so they will cancel out, right? Because I am adding and subtracting the same signal here. Is it clear first step? Okay, I hope it is clear. Then what I can do, because I want only unit feedback, right? So I will keep this one and I will add this one with this one. Okay, so then what will happen? GS, and this is plus, this is minus. These two can be added because both are subtracting, negative sign here. So we have H minus 1 here, right? And I am picking that signal 1 here and this minus sign, and this is output Y. Okay, is it clear? Now we just apply this feedback formula for this inside one, this. Okay, so then what will happen? This is R plus, and this is what? GS by 1 plus G into H. So what is this? G by, this is G, H is H minus 1 here, so 1 plus G times H minus 1, right? This transfer function for red one that I have enclosed, which is equal to G by 1 plus GH minus G. Is it clear? Okay, is it clear till now? If you have any doubt, you can ask. Is it clear? Okay.
Sir, explain once again.
Okay, I will explain. Okay. So your steady state formula are applicable for only unity feedback system, right? Non-negative unity feedback system, right? So that means your HS should be 1 there. Okay, yeah. Anyway, I'm explaining. Okay, so somebody is asked. Okay, so your unity feedback system, like you need HS to be 1. Okay, so you are given here HS value something else, right? Not 1. So you have to transfer the system if you can find some equivalent representation. Okay, what I'm doing is I'm finding some equivalent representation where this is something kind of like let G dash S and this is 1. Okay, this is 1, this is minus here, so you have input output. Can I transform this system in the original one to this one? Okay, with some G dash with unity feedback system. Okay, HS equal to 1, then I can apply formula directly, right? Is it clear?
Yes, sir.
Okay, so that's what we are doing here. Okay, we are given some system with HS which is not equal to 1, then we can whether we can transform it to some this system, second one, this one. So once we have this G dash formula with unity feedback, then we just apply the direct formula whatever we have learned for steady state error. So that's what we are doing here. So what do we do? We added and subtracted the same signal, -1 here and 1. Okay, so because both are negative signs, so here subtracting, so -1 and 1, so they will cancel out, right? These signals, they are added at this point. Okay, I'll mark it this point. Okay, is it clear? These two signals will cancel out, right? I can add and subtract that.
Both positive and negative, sir.
Yeah, okay, because I have subtracting them right here. Okay,
Okay.
yeah, I'm using the same sign here, minus minus. Okay, so I'm just changing the sign here in the gain.
Okay.
Yeah, you can do whether you can add or subtract anything. Okay, I'm using the same sign here in the addition here, minus sign, and I'm just changing the gain. Okay, so that they will cancel out. Okay, up to this is it clear? So then,
Yes, sir. Clear after
yeah.
this.
So then we want this lower block to remain there, right? Because we want this unit feedback there. So we just simplify other ones, this -1. So what we can do is, because this -1 and HS are added to the same time, right? I can merge these two addition blocks, right? This one and this one, because they are added, I can merge them. HS -1 I can do because both signs are negative. Okay, here. Is it clear? Because if you have, okay, you remember this, right? First question. Okay, let's be there. In the first question here, these two addition are there, so I can just add them, right? This is what will be S plus 1 by S, right? Because both signals are added to this, right? It is clear? Okay.
Yes, sir. Clear.
Yeah, so for same thing I am applying here also. Okay, in that what, yeah, here, because okay, this green color mark this, these two signals are subtracted here, right? HS and 1 -1, so I can just combine them, so it will be HS -1, right, which is subtracted here. Is it clear? These green ones,
Okay, sir. Up to this clear.
yeah, so that I can combine, right?
Yes.
Yeah. Just again try this. Okay, if it is
Okay.
not clear. Yeah, so then this red one that I have already there, this one, I just simplify that block. Okay, so that is what GS by 1 plus GS minus GS into H minus 1, right? This one. So this is what G dash, what we desired there, right? Is it clear?
Okay.
This inside term, okay, this red one, because this is just a feedback loop, right? Okay, this
Okay,
red,
sir.
this red one without 1, I can simplify that, right? I have GS and this HS value is this H minus 1. I can simplify the feedback formula I can apply for inside loop. So this is what we get.
By combining.
Yeah, by combining them, right? Because this is feedback.
Okay. Okay, sir.
Yeah, this is positive and this is negative here, right? Yeah.
Yes, sir. Yes, sir.
So you just use that formula. This is formula, right? G by 1 plus GH. But instead of H, we have H minus 1 here. So
Because we have that
yeah,
pH minus 1 is there.
so that apply this here.
Okay.
Yeah, so this is
Okay, sir.
1 plus G into H minus 1 because H minus 1 is there. Okay, so you have G by 1 plus GH minus G, which is the G dash that we want to find, right? Then the system is simplified to this one.
Okay, sir. After simplifying that, G1 plus GH minus G is come out.
You understand that, right? How you get?
Yes, sir.
Yeah,
Yes,
okay.
sir. Yes.
Yeah, then you just find this G by 1 plus GH minus H, right? Then you can apply the steady state formula. Okay, so that's again just plug in that value and I will write here. I just have to simplify, nothing else is there. So you want to find what? G by 1 plus GH minus G. Okay. So you are given G to be K1 by S into S plus 1 plus GH K1 by S plus 1 times 1 plus K2S minus K1 by S into S plus 1. Okay, so it will be K1 by S into S plus 1. So you have S square plus S plus K1 plus K1 K2S minus K1 by S into S plus 1. So it is K1 by S square 1 plus K plus K1 K2 S, right? This will cancel out. Okay, so I can take common K1 by S into S plus 1 plus K1 plus K2, right? So your type 1 system, and for that you know what is steady state error, right? Is it clear? Okay, so I am assuming it is clear. If not, you can ask. Okay, once you know that it is type 1 system, then you know that yeah, okay, so yeah, it's clear, right? Type 1 system, your unit step response, that is the steady state error for unit state response will be 0, right? Okay, so then we move to next question. So you are given force system ABCD, okay, with some pole location. Then you have to identify the system which has the maximum damping and the minimum natural frequency. Which system has the maximum damping and which system has the minimum natural frequency. Okay, you can answer through poll. Question 9. Okay. Okay, so you can answer through poll, then we will discuss. Yes, you have any doubt? Yeah. Okay, so okay, let's discuss this. Okay, So you are given pole location and you have to find like system with maximum damping and natural frequency, minimum natural frequency. Okay, so just let draw these signals. Okay, what is the relation between these poles and damping ratio, natural frequency? So you already know that poles location are what, for second order system. Okay, so let me explain this, then I will go to your question. Okay, so this is omega d, or you have omega n into 1 minus this, right? This is the location of your poles, right? So because we have given dominant pole, so you can just think of it as a second order system. Okay, so second order system with this pole location as a complex conjugate poles are there. So just draw this picture. So you have this complex conjugate poles with this as an minus eta omega n, and this is omega n. So this is imaginary axis and this is the real axis. So you have omega n into 1 minus eta square. Okay, square root. Yeah. So then what is this length of this? Can anyone say? You have a triangle, right? So you can find this what is this called, diagonal element. I don't know what is called diagonal, right? This, you have this value as zeta omega n, and this is this value omega into 1 minus zeta square root over, right? So this point will be what? The square of this, right? Addition of this, which, huh? Right, it's clear. I'm just calculating this point. So this will be this square plus this square, right? So this below square is what? This one, and this one is this square, this one, so square root. So we have, just put this bracket here. So it will be omega n square, right? So this is omega n. Let's draw it properly. Okay, I'll just draw it properly. This is minus zeta omega n. This is omega n times 1 minus zeta square root. So this will be omega n, and this angle, what is cos theta then? Can anyone answer? Okay, so yeah, zeta, right? So we can find zeta and you can also find omega n, right? So for each of the system, once these poles value are given, right, you are given this value, that is the, you just compare with this form. This is the pole location, right? What we have drawn here. Is it clear up to now? From that pole location you can directly calculate your omega n damping ratio, right? So let me just show for one how to calculate. Okay, for first system A. Okay, so A you are given minus 3 plus minus j5. So this is what? This is minus zeta omega n plus omega n times 1 minus zeta square. So you see that you just square and add these two terms, then you get omega n, right? So for this system, what will be what? Omega n will be then what whatever this value is 3 square plus 5 square 2. Okay, 5 point something here coming 5.83. Is it clear? Okay, is it clear or not? Okay, you can ask. Okay, if it is not clear, how you are getting? Yeah, okay, yeah, okay. So I'm assuming it's clear. Okay, but two guys have answered clear. Okay, so this is how you calculate omega n, and similarly you can for system A. I'm calculating this, so I can also calculate zeta to be cos theta. Okay, but cos theta is equal to I can also calculate this this by omega n. That means the absolute value of the real part, this one, by omega n, right? So I'm let it denote by minus sigma d. Okay, so we have sigma d, the real part, by omega n. Omega n is this, we already calculated here. So it is 3 by 5.83. This is 3 by 5.83. So you just compute this for all systems. Okay, like that. Okay, so then you can compare the system which is the maximum damping and the minimum natural frequency. Okay, is it clear? So I'm not going to solve it because it's just straightforward then, right? Okay, just okay, I can also write this, not a problem. So for A system, so we'll write omega n, and okay, first I will write damping, and this is omega n. Okay, so I'll just write for each one, you can just verify. So for A this is pole is, okay, let me write it A, and pole location this is, okay, so it is minus 3 plus j5. So then omega n will be this formula, right? You just square and add them. You just remember this diagram. Okay, so it is what we calculated 5.83, and zeta we have calculated the real part by this omega n, which is 3 by 5.83, which is 0.5146 something. Okay, for B you are given minus 5 plus minus j4. Again you calculate omega n first, which is square root of 5 square plus 4 square, which is 6 point something, okay, 6.403, and zeta will be real part, which is 5 absolute value by 6.403. okay, it is 0.781. Similarly for C, minus 12 plus minus j1, so it is omega n 12 square plus 1 is 12 point something, 12.042, and damping ratio is real part, absolute value of real part 12 by this omega n 12.042, so which is 0.9965. D we have minus 1 plus minus j6. So again omega n is 1 plus square root of 1 plus 6 square, right? So it is 6 point something, 6.0828, and damping ratio is real part, which is 1 by 6.0828, which is 0.144. okay, so then so the maximum damping ratio damping is what, for what the damping is, you can see for C, right, this one, and the minimum natural frequency, which is this one for A. Okay, so answer is C and A. Okay, okay, so then we move to the next question. Okay, so you are given an unity negative feedback system with forward transfer function, feed forward transfer function, GS value this. So for what value of K, the closed loop response will be as shown in the figure. Okay, question F10. Okay, yeah, you can answer through a poll. Okay, so yeah, I'm seeing your question. What to see? Closed loop. Okay, the closed loop equation is this: how many closed loop pod had real part minus one? Okay, so what you do, you shift that. You know how to shift, right? Okay, Pritham. Yeah. Okay, so for your question, so how many poles does it have with real part minus one? So what you do is you shift that s, okay, with such that its origin will be shifted to minus one. Okay, the hint will be what? So you shift this, you transform your s with something like s dot, okay, s prime, such that s prime, in the s prime your equation will be such that your origin will be in minus one, right? Yeah. Then you apply, like for what value you have this, you apply this like checking that out Horwitz criteria. Okay, for Horwitz criteria, you know if your poles are in the diagonally opposite or in the imaginary axis, you will have a row of 0, right? And from that you can have, like if diagonally opposite, right? Then pole for that, if a row of 0 is there, then you know that for all below that pole, like below that row, whatever you are solving, it follows only that diagonally opposite poles, right? Is it clear till now? Okay, you have okay, written some. Okay, try to solve this method. Tell me. Okay, replace s by s plus 1 and apply the, yeah, that is one method you can apply. Okay, other methods, I don't know if we can solve for other method, but that will be the easiest one. Okay, I will check if there is other method, because I don't know if there is other method. Okay, like if I were you, I will do that method. Okay, I will check and will get back to you if there are other methods. Yeah, so to answer your question, I don't know if there is other method, so I will just check and see if there are other method to find this. Okay, yeah, so then we come back to our problem. Okay. Okay, so we just discuss this question 10 again. So what you have to find, k, right, for closed loop system. So you are given g as this feed forward transfer function. You have to find this k value so that this response is like as shown in the figure. Okay, so what you do, then you just find the you are given peak overshoot, right? Here already have peak overshoot, so you can find this damping ratio from there, right? Okay, so first we write the closed loop transfer function for this problem, because you have a okay, unit feedback system with gs this one, so your closed loop system will be what? G by 1 plus gh, h is 1, right? Unity feedback given. Okay, so then closed loop will be simple, k by s into s plus 3 1 by k by s into s plus 3, so you have k by s square plus 3s plus k. Okay, so and okay, so then from maximum overshoot. Okay, so what is this maximum overshoot here? Okay, I'll write mp equal to 0.5266. okay, from this maximum overshoot I have already written the formula for damping, right? Here, this one. you can find the damping ratio from this maximum overshoot, right, using that formula. So let's just calculate this damping ratio. You are given maximum overshoot, so you can find the damping ratio here. So for this I'm just calculating it to be minus logarithm of this value. This overshoot is given 0.5266, right, by square root of pi square plus this ln times 0.5266 square, right. I'm just using this formula. I'm again writing that, okay, here. This is equal to minus ln this by square root of pi square plus ln square mp. Okay, I'm just using that formula to calculate this because we already have this mp value here. Okay, so just let me calculate this. It is 0.5266. okay, so it's coming around 0.2. okay, 20. So we have zeta value, this one. So once we have zeta value, this 3 is what? In the standard form it will be, okay, omega n, right, square by s square plus 2 zeta omega n s plus omega n square, right. So we can find omega n from this term, right. So we have 2 zeta omega n equal to 3, right. Just compare the coefficient of s. So from which I can find omega n to be 3 divided by 2 times the zeta, which I found to be 0.2, which is 7.5. okay, omega is equal to 3 by 2 zeta equal to 3 by 2 into 0.2, which is 7.5. okay, so once we have omega n, then you know what is the value of k, right. K will be equal to omega n square, so it is 7.5 square, so you have 56.25. okay, is it clear? Okay, so any doubt? Okay, so I hope it's clear. Okay, yeah, okay, so then if you have any doubt you can ask, or what do you ask? Okay.